We're going to talk about determinants for a little bit, because in order to understand surface area, in order to really understand surface area, it kind of helps to understand something known as a Jacobian determinant. Right? So what, or just the Jacobian for short. So what I figured I would do is just kind of take us back to the concept of a determinant. We'll talk about it numerically because we focused on it a little bit. For those of you who have experience with linear algebra, you have plenty of knowledge of this stuff. The applications of it may be somewhat limited to the theoretical, but what we want to do is try to apply it, you know, so get some of the practical understanding, right? So in order to do that, we need to kind of rewind, talk about determinants a little bit, discuss the computational aspects, and then go from there. Right? So for a 2x2, you see the example. 2x2 matrix, the determinant gives the area of the parallelogram created by two adjacent vectors. We talked about that in the second unit, maybe even the first unit. I lose track of these things. So the example here is find the area of the parallelogram whose adjacent sides are represented by 2, 1, and 1, 3. Right? So that example, you could actually do that by rote computation. You could find a cross product. You can do a whole bunch of different things that, you know, the magnitude of the cross product. But what we're going to do is go on down to the definition of a determinant and use that approach to figure it out. All right. So this is the cofactor definition of a determinant. And what that tells us is that we have an alternating relationship in terms of powers of -1 based off of the position within the matrix. And that creates an expansion. And once you have your expansion, we figure out the result, the determinant of the smaller matrices. In the case of a 2x2 matrix, that's not really very challenging, but I can show you using a 2x2 matrix just how it works. It's kind of interesting even on the smaller level. So we have this formula, and the notation is kind of weird, but the A represents, the lowercase a represents the position, the uppercase A represents the name of the matrix. So when I say the sum from j equals 1 to n, it's always in the form of A sub ij, where I is the row position and j is the column position. All right. So if I'm telling you that j is going from 1 to n, I'm saying that j, the column number, is increasing from 1 to 2 to 3 to 4 to 5 on to however many columns there are in the matrix. All right. So, and then we would add all that stuff up. So let me take you through using the formula just to kind of give you a little bit of a taste. So this is telling us if we focus on j equals 1, so that's not a j. J equals 1 to n. We have -1 raised to the 1 plus j multiplied by a sub 1j. All right. Now that little piece there, this little guy is very subtle, very, very inconspicuous. That's saying that we're working in row 1, but that we're allowing the column to vary. All right. We're multiplying by the determinant that's formed based off of matrix A, row 1, column J. Doesn't matter what column. All right. We're going to do it one at a time anyway, so it doesn't make a difference. All right. So the expansion for this. So first off, I would start with column 1. All right. So I would say -1 to the 1 plus 1, which would imply that we're looking at a sub 1, 1, row 1, column 1, multiplied by the determinant based off of matrix A with row 1, column 1. right? So that's what we're starting with, and then we kind of build off from there. So let's focus on that. First off, -1 to the second power is just going to be a 1. A sub 1, 1. That's the entry in row 1, column 1, just the number itself. All right, so that value here is 2. Then I need the determinant based off of the matrix formed if we remove the row and column that A sub 1, 1 is in. All right, so this is out, this is out. Now, since it's just the number 3, that's it. All right, that's all that's left over. All right, what I'm going to do is I'm going to duplicate this real quick. So I could draw another diagram in a sec. Just kind of chuck it over here. So we can multiply that out, but we're going to get a 6 as a result. All right. I mean, you didn't even need to tell you. So now let's continue the expansion and say that we have -1 to the 1 plus. Now I'm going to go a different color. Well, I'll use the same color, doesn't matter. 1 plus 2, because we're now in row 2. All right. So that would be multiplied by A sub 1, 2. So the entry in row 1, column 2. All right. And then multiply that by the determinant that you would get, or the value of the matrix that you would get if you remove the row and column associated with the entry 1, 2. All right. So in this case, we're looking at -1 to the third power, which is a -1. A sub 1, 2. Row 1, column 2 is the number 1. If you remove the row and column that it's in, that leaves you with just the number 1. And so you end up with 6 minus 1, which is 5. Okay. And so that's your determinant. And, you know, it's a lot more work than you would really think is necessary, because if you remember, for a 2 by 2 matrix, we talked about this before, it's diagonal down minus diagonal up. Right? Multiply down the main diagonal, 2 times 3 is 6. Multiply up the other diagonal, 1 times 1 is 1. Subtract the 2, 6 minus 1 is 5. It's like, what's the deal with all this? What's the deal with all, you know, so it's kind of leading us towards something, because we got to be able to do this with partial derivatives in a couple of minutes. So it's gonna spice things up somewhat. Okay. So when we want to find the determinant of a 3 by 3 square matrix, it's really going to be the same idea. We're still using this determinant aspect, this determinant relationship. Aspect was not correct. So same rule, row 1, working across row 1. As it turns out, and I don't want to do too much linear algebra, I need to do enough of it for us to understand why this stuff works the way it does for our Calc 3 business. But the determinant will work if you go across any row, right? So if I wanted to see how I have the fixed value of A sub 1j, it could be A sub 2j, it could be A sub 3j, right? A sub 4j, depending on how many rows or columns there are. So the benefit of choosing one row as opposed to another has to do with the values, right? Because if you have a lot of zeros in a particular row, that's the row you want to use to determine your cofactor expansion, right? So in this case, what I'd be looking at first, again, row 1, column 1. So my J value is 1. We start off with a J value of 1. So that would be saying -1 to the 1 plus 1 power times that first entry, which is 1, times the determinant of everything that would be left over if you removed the row and column that contained that number. So let me duplicate this real quick. I'm just going to chuck a couple of them in here, just so I have it. All right, and I'll bring this back in. There we go. All right, so if I remove the column and the row that contains this value, I'm looking at 1, -1, 2, 0. All right, but then we got to do it again, this time for the second entry. So if I'm looking at the second entry, that's row 1, column 2, so -1 to the 1 plus 2, multiplied by 5, multiplied by the remaining matrix when I remove the row and column that contains that number 5. So 0, -1, 1, 0. All right. So then one final part of the expansion plus -1 to the 1 plus, now we're in row 3. The relevant value is -4. Remove the row and column that contains the -4. Let me do a little shrink-a-dinky. And we're going to have 0, 1, 1, 2. So I got the -4 and then 0, 1, 1, 2. All right. Now, I don't want to have to expand my expansion, because in number 1, we use the expansion technique to figure out what the determinant was for 2, 1, 1, 3. But we basically just confirmed that that's giving us the rule of diagonal down minus diagonal up. So we're just going to use that now, right? So 2 an even power becomes a 1 times 1 times diagonal down is 0 minus a -2, so +2. So a result of 2. Then raised to an odd power, -1 times 5 times diagonal down is 0, diagonal up is -1. So 0 plus 1, result -5. And then for the last bit there, it's raised to an even power, so a +1. We got the -4. Diagonal down is 0, diagonal up is a +1. So 4 times -1 is 4. So the sum of these values gives us a result of 1, and that's our determinant. All of which can be verified using the calculator, which I'm going to remind you how to do in a second. But that's just a kind of a gist of how you go about doing it by hand, right? Because we're going to need a little bit of understanding of how to do it by hand in order to understand the Jacobian. Quick aside, positive, negative, positive on the expansion, alternating series, right? So that summation expands to an alternating series, and there's that gives us a justification for why our IJK coefficients always alternated in sign when we were finding the cross product, right? Because we are in fact finding the determinant of the 3 by 3 matrix. Right? But like I said, a quick refresher on how to find the determinant using Desmos. So desmos.com. Math tools, matrix calculator, new matrix, automatically defaults to matrix A. I'll do number 1 first. 2, right arrow, 1, right arrow, 1, right arrow, 3. Hit enter, locks it in. And then we just want determinant of matrix A, and it spits out the 5. If you want to continue on using the same Desmos, select new matrix, it'll automatically define it as B. So you just got to remember to find determinant of B. This one's 3 by 3, increasing number of rows and columns. So 1, 5, -4, right arrow, all the way. 0, 1, -1, 1, 2, 0. Enter to lock it in. Determinant matrix B gives you the 1. So pretty straightforward, pretty solid, not too difficult there. All right. So that's your quick and dirty refresher on determinants. And you know, the hope is that you get a little bit of a reminder of just, you know, okay, we know how to do this, number 1. But number 2, there is those little quirks, the little intricacies related to the changing in sign, and it's like, oh, what was that all about? And now you kind of have a better sense, hopefully. All right. So to the next page. Honestly, no idea why I put any of this stuff here. This might have been just for fun, because this is really just explaining to you why you're allowed to work. You know, we just did row 1, but you could work row 1, 2, 3, whatever row you want, holding the row constant, just working across the columns. This is kind of overkill. Yeah. So I think maybe I just went a little nuts copying from my linear algebra notes. So yeah, it's a little, like I said, a little bit overkill. I don't think, yeah, there's really no need to use that for Jacobians. So, yeah. Yeah, you know what I'll do? Just so it's not a waste. Put a star on these bad boys, and we'll come back to them next time. But the triangular matrix theorem is pretty cool. The product of the entries along the main diagonal, if it's a triangular matrix, whether it's upper or lower triangular, the product of the values along the main diagonal will end up being the determinant. That's kind of a cool relationship. And you know what I'll do, just to kind of make this worth our while. I'll actually take you through the cofactor on this one, because it's pretty cool. All right, so 1 times 2 times 3 is going to give you a 6. Let me show you, aside from what Desmos would say, let me show you how that, or why that works the way it does. So let's say, because what I was saying before is that you want to work along the road that has the most zeros in it, right? And so in this case, it would make sense to let I equal 3, because that puts you in the 3rd row. That's the one with the most zeros. So what I would say is, based off of that cofactor relationship, that the determinant of A is going to be equal to the sum from J I keep doing my J's backwards. They keep looking like I's for some reason. J equals 1 to n of I, negative 1 to the 3 plus j multiplied by a sub 3j multiplied by the determinant of a sub 3j. So we're holding row 3 constant. The benefit of doing it this way, again, is taking advantage of all those zeros. All right, so we'd be looking at negative 1 raised to the 3 plus 1 multiplied by 0. All right, because if, again, we're working across the rows, this would be my first entry, multiplied by 0, multiplied by the determinant of a sub 3, 1. Third time's the charm. All right, which zeroes out. And I would do the same thing, negative 1 raised to the 3 plus 2 multiplied by 0, that's my second entry in row 3, multiplied by the determinant corresponding with 3, 2, still zeroing out. We still want to kind of sort of do it, at least with this in mind, because we're going to have that alternating sign relationship, and we want to be mindful of that. All right, so the last one would be negative 1 raised to the 3 plus 3 multiplied by 3 multiplied by the matrix that you would get if you removed the row and column containing the 3. So 1, 19, 0, 2. I'm going to reduce the size here a little bit. It'll look a little bit better. All right, so this zeroes out. This zeroes out. This last bit, we're going to end up with a 1 multiplied by 3 multiplied by diagonal down, which is 2, diagonal up, which is 0. 1 by 3 by 2 gives you a result of 6, which is what we got by multiplying down the main diagonal. Even though the cofactor expansion wasn't that complicated in this case, it's still a whole lot easier to multiply down a diagonal if you can. So as long as you recognize something is triangular in terms of a square matrix, then all that means is that the non-zero values are at, kind of using the main diagonal as a boundary, and everything on the other side is just 0. So zeros on one side of the main diagonal and non-zero values on the other, then you could just multiply down the main diagonal. That ends up being a pretty nifty shortcut. Right? And so if you're savvy enough, when you use your cofactor expansion, you can kind of make use of that. Like in number 4, I would be looking at this as like, well, I'm definitely working with that last row. I'm not working with any other row because that one only has one non-zero value. Right? It makes life a lot easier. All right. So let's talk about Jacobian determinants a little bit. We're not going to get through all of it because it's a pretty hefty topic. But we can at least touch on it, at least get started. So Jacobian matrix is a matrix of all first order partial derivatives of a vector value function. All right. So we also have the real valued functions of 2 and 3 variables, which can be thought of as respectively as these expressions. All right. So the real valued functions in 2 or 3 variables is really just, if you're creating vector value functions related to the first order partials, then this is how it would necessarily play out. If it's in 2 variables, The only way you can take the derivative would be with respect to x or with respect to y. If it's in 3 variables, you can go the distance, right? We will circle back and talk about this next class, but this is a symbol for the gradient. All right, and we'll talk about what that means, but it's pretty useful stuff. I mean, it's very useful stuff. I don't want to oversimplify it. All right, partial derivatives of these functions, if they exist, can be organized in an n by n matrix, the Jacobian matrix of J of f, as follows. All right, so you can see that we're taking all of our partials and putting them on down the line in the form of a matrix. All right. So I'll just read the blurb to you because it's lengthy, but it does a better job of explaining it than I would. I mean, partially my words anyway. But the Jacobian determinant, often simply called the Jacobian, is the determinant of the Jacobian matrix. So determinant, right? So why are we talking about determinants? Well, we want to have the simplest way of computing a determinant, because if we're going to be working with expressions rather than just numerical values, then simpler is better, obviously. The Jacobian of a function describes the orientation of a tangent plane to the function at a given point. In this way, the Jacobian generalizes the gradient of a scalar valued function of multiple variables, which itself generalizes the derivative of a scalar valued function of a scalar. The Jacobian can also be thought of as describing the amount of stretching that a transformation process imposes. For example, if you have a function x2, y2 that maps to f of x1, y1, that could be used to transform an angle. The Jacobian describes how much the image in the neighborhood of x1, y1 is stretched in the x, y, and xy directions. Right? So it's given you basically the stretching aspect of that transformation. Right? So if I perform some kind of transformation, reflection, dilation, rotation, whatever, or glide reflection or something like that, then the Jacobian will tell me how much stretching happened in that process. Now, if there's no stretching, then we're talking about a rigid motion, right? So that's useful information. If the function is differentiable at a point, the derivative is given in coordinates by the Jacobian. But a function does not need to be differentiable for the Jacobian to be defined, since only the partial derivatives are required to exist. Right, the importance of the Jacobian, so this is obviously an important sentence, it says it right there, lies in the fact that it represents the best linear approximation to a differentiable function near a given point. Right, so it's kind of weird, but looking in 3 dimensions, you wouldn't be thinking about a linear approximation as being a meaningful thing, but a Jacobian will give us the best linear approximation to a differentiable function at a specific point, no matter what the dimensions are. In this sense, the Jacobian is the derivative of a multivariable function, or a function of n variables, n greater than 1. The derivative of a numerical function must be matrix valued or partial derivative. Right? So then, yeah, you have some other information related to the linear mapping, the linear approximation, but that kind of gets at the idea of the concept of a Jacobian, where you're talking about transformations, you're talking about linear approximations in 3 dimensions, 4 dimensions, 10 dimensions, whatever, but it's all based off of partials, all right? And so that's where we're at this point, all right? So let's hop on over to the next page and see what's going on here, because we want to be able to talk about this with respect to not only Cartesian coordinates, but we want to be able to talk about it with respect to spherical coordinates. All right. So the blurb here is really kind of like just reiterating a lot of the stuff I just said, but it gives us, if we perform the appropriate transformations, it gives us this relationship, and that is the Jacobian matrix for any coordinate change from rectangular. I lost the word there for a second. Sorry, rectangular coordinates to spherical coordinates would be partial with respect to x, I'm sorry, partial of x with respect to rho, partial of x with respect to theta, partial x with respect to phi. And then the corresponding transformations are based off of the substitutions that we learned about last class, right? So that's something that you can kind of hold on to as fact, because really what's happening here is, and you can do the work if you want, I just figured I wouldn't bore you with it. But if I were to take the first order partial of this with respect to rho, this is what I would get, right? If I took the first order partial of this with respect to theta, this is what I would get. If I took the first order partial of this with respect to phi, this is what I would get. And we just kind of go down the line with that, right? So like I said, I didn't think it would be necessary to bore you with all of that. But we could also do it with rectangular coordinates. We're just working, again, one variable at a time, right? Now, the thing that you got to keep in mind is sometimes when we go in multiple coordinates, I'm sorry, multiple dimensions, we tend to go subscripts, because if we're not limited to 3 dimensions, we kind of run out of letters pretty quickly. So when I say x sub 1, x sub 2, x sub 3, we could think of this as x, y, z. All right. So don't get thrown off by that. This is really, for example, this would be the same as y equals x. This one would be the same as, well, y2. That's just really, if you're just coming up with a designation, that's just a second y equation. So that's not really anything too earth-shattering. That would be y equals 5z, right? Because the third x, the subscript of 3 related to that x is going to be the z variable, right? The next one you could think of as, I won't write same as again, y equals 4y squared minus 2z. And then the last one, y equals z sine of x, right? So a lot of stuff going on there. You know, it gets kind of messy. But when we say take the derivative with respect to x sub 1, all we're saying is take the derivative of this function with respect to x. Derivative of x is 1 with respect to x. But then do it with respect to y and z. Well, if I take the partial derivative of an x function with respect to y or z, well, x is treated as constant. Derivative of constant is 0. All right, so all that stuff would 0 out. So then in the second one, we're taking the derivative of 5z with respect to x sub 1. That's the same as taking the derivative with respect to x. Well, 5z is treated as constant, so the derivative of 5z would be 0. With respect to y, same deal. The derivative of 5z with respect to z would be 5, though. In the third one, we're taking the derivative of this function here with respect to x. There's no x there, so that whole thing is treated as constant, goes to 0. Taking the derivative with respect to y, the negative 2z goes to 0 because it doesn't have a y in it, but 4y squared differentiates down to 8y, or x sub 2 if you want. Right? And then same idea, when I take the derivative with respect to z, the 4y squared doesn't have a z in it, so that goes to 0. The negative 2z would go to a negative 2. And then that last function, x equals zx squared, you got to use the, well, let's see, this is with respect to x. So we're using the constant multiple rule, so we hang on to the, little typo for somebody. All right, so we're looking at the zx z sine x should have become z cosine of x. So this should be a 3. All right. Typo for somebody. All right. There's no y in this expression, so it does go to 0. When we take the derivative with respect to z, the z part of it is going to go to 1. The sine of x is going to remain the same. And so there you go. So that this whole thing here is the Jacobian matrix. All right. So I just want to see. Oh yeah, I got lazy. So what we would do at this point is we would find, and this will be the. No, I was going to say this will be the last thing we're going to do. We don't have time for it, so we've already done the last thing we're going to do. So what we would have to do is find the Jacobian determinant. Okay, so what I'll ask you to do is find the determinant of the Jacobian matrix. All right, so that matrix that we just developed there, find the determinant of that. So that'll be one of the start problems. And then the next one would be on the next page here, this example. All right, and then I'll kind of get at what the heck this is all for when we talk about that next example next class, and then we'll talk about surface area. And that should probably be it for the course. All right, so we're kind of there. We might do a little bit with vector fields, but we're not going to do a whole heck of a lot. All right, so all I'm going to ask you to look at is the finding the Jacobian for this, so the determinant of the Jacobian matrix, and also look at the problem, the example on the next page. All right, so let me stop the recording.